Good morning and welcome to ERDC Live. I'm your host, Shelley Tingle with the U.S. Army Engineer Research and Development Center. Today we will discuss ERDC's cutting-edge fiber reinforced polymer, or FRP, research and the impact it is having on extending the life of our nation's critical infrastructure, from repairing cracks and alleviating corrosion on steel structures to facilitating the construction of more resilient critical components. FRPs are a more sustainable and cost-effective solution to several demanding challenges. ERDC's FRP research is enhancing the structural integrity and sustainability of military and civilian infrastructure and demonstrating the potential to revolutionize traditional engineering practices. We are joined by Dr. Guillermo Riveros, a research civil engineer with ERDC's Information Technology Laboratory, to discuss how ERDC is working alongside engineers from across the U.S. Army Corps of Engineers to incorporate FRP's unique capabilities into a wide range of projects across the nation. Dr. Riveros, thank you for joining us today.
Thank you, Shelley, for the invitation.
Glad to have you. So we're going to start from the beginning. Can you explain to our audience who may not know what is fiber reinforced polymer and what issues these materials are helping address?
Well, first of all, as the word says, it's a fiber, small fibers that are linked together to create a composite. And once they're put together, then we add some epoxy to make the fibers stand together and be stronger. So it becomes stronger. So what are we fixing or what are we repairing nowadays with these fibers? And in fact, we have two types of fibers: basalt fibers that come from a volcanic rock, or carbon fiber that are extremely strong. Both of them are extremely strong. In fact, stronger than the steel. If we think about it. So the two main problems that we have are the two main deteriorations that our hydraulic steel structures have, which is fatigue cracking and corrosion. So with fatigue cracking, what this fiber does is that reduce the crack opening displacement and therefore reduces the stress intensity in the crack tip. Therefore, that crack is completely arrested, so it doesn't continue growing. However, the district offices sometimes, when the cracks are too long, and we suggest to do that, we use a traditional method, which is gouging the crack, welding the crack again. But on top of that, because we know the stresses that cause that initial crack are still existing, by adding that additional level of fibers, one or two layers of carbon fiber or basalt fibers, then we also strengthen the structure. Therefore, the stresses on the steel are reduced, and therefore that crack will never happen again.
Wow, that's a great solution.
Yes.
Can you describe the current state of hydraulic steel structures and the common challenges they face? How does FRP help address these challenges compared to the traditional methods? So you just talked a little bit about that, about corrosion and fatigue cracks. And so what is the state of our current structures?
One important aspect is to recognize that almost between 60 and 70% of our navigation steel structure, hydraulic steel structures, have already passed their design life, the 50-year design life. Therefore, like everybody else, that you get older, you start getting problems. So that's the same situation that we're having with our structures. So the main two issues are corrosion and cracking and fatigue cracking. And therefore, by using this methodology, we are doing two things. With the fatigue crack, we already discussed that, but with the corrosion, we have discovered in the research that we have done that we can bring the structure back. If it has up to 30% corrosion, we can bring the structure back to the original stress state of stresses. So that is a significant amount of a gain. Additionally, we sometimes it's not enough time to build a new gate. It takes perhaps a year or 2 years. So therefore, by using these fibers, it can be a fast solution to have a quick repair and allow that structure to sustain the loading for 2-3 more years while the new structures come into play or are built or made. So.
Absolutely amazing. So I want to ask our audience who are watching live, those of you who are watching live on YouTube or LinkedIn, you are part of the conversation, and I know you're going to have lots of questions for Dr. Riveros, and so just put them right there in the comments, and I will get to those momentarily. And so what are the common types of corrosion and section loss found in hydraulic steel structures, and how does all of that affect the structural integrity?
Yeah, the most common is two main common corrosion is the cathodic corrosion and also pitting corrosion is a significant amount. And the pitting corrosion is pretty much holes in the structure. It's like somebody ate a piece of the steel and it's many holes. So pitting corrosion. And then the cathodic corrosion is more uniform type of corrosion. And what it does is eating the steel. And by eating the steel, that means that the cross section or the thickness of the steel is diminished. Therefore, the strength of the plate that was designed for a particular amount of loading, therefore, is carrying much more loading. And that's why sometimes it becomes, overstress. So that's kind of the situation. With the FRP, because it's, like I mentioned, basalt fiber and carbon fiber are much stronger than the steel. The carbon fiber has 10 times the strength, the tensile strength of the steel, and the basalt fiber is 5 times the tensile strength of the steel. So with that capabilities, then we can strengthen those cross sections and bring it back to the original stress.
And bringing it back to the original strength, that's pretty impressive. Yeah. Saves a lot of money. So what are some of the practical challenges and considerations when implementing FRP repairs on hydraulic steel structures?
Well, the main challenge is that we have to do these repairs on the dry. So we need the lock chamber to be underwater, so dewater. So that's one of the reasons that we wait for the dewatering process in the different lock chambers or the different locks to go ahead and do the repairs. So 1 or 2 repairs per year, perhaps. Mm-hmm. But we have been successful enough to perform about 12 to 13 repairs in different gates. But the challenges are we need to clean the surface all the way to the base metal. Okay, and this cleaning is done either by grinding the steel to the base metal or by sound blasting. Many researchers have found that by sound blasting, the atoms of the steel become very happy and ready to adhere very well. And when you sound blast, it appears that the adhesion with the epoxy and the fibers is much better than when you grind. However, in many cases, you cannot sound blast, so you just have to go along with the grinding.
Yes. Well, that's amazing. I was talking to you earlier about we enjoy having happy atoms. When the atoms are happy, the FRP sticks and everybody's happy. And so I want to go back to what you were saying about the FRP installation and compare that to what are the traditional methods. So how is it different than the traditional method, and is it more expensive or is it less expensive? What are the differences between them?
I mentioned the traditional method a little while ago for fatigue cracking,
yes,
which is gouging the crack and re-weld. However, the fatigue life doesn't reset to 0. So even though you gouge and re-weld, the metal has been already fatigued for a certain amount of cycles. And what happened with welding is that sometimes a short period after the welding, the crack starts once again. That's one issue that we have. That's a traditional method. Another traditional method is drilling holes in front of the crack tip. That works very well when it's just a perfect horizontal or perfect vertical crack, meaning it's a bending crack or a pure tension crack is what we call it. However, our structures, the state of stress of our structure is what is called a mixed mode loading, which it has tension plus shear.
That's right.
And those cracks grow between 30 and 60 degrees. And you see the majority of the cracks on our gates grow between 30 and 60 degrees. If you drill a hole, instead of stopping the crack from growing, you are actually extending the crack, and that crack will continue growing. Therefore, that is not a methodology that always will work, and in many cases, it won't work for the state of stress that our structures are subjected to. Therefore, by adding the FRP, it becomes a more reliable. A couple things are important in here. Another traditional method is to put plates to strengthen the cross section and bolt plates.
That's right.
Okay, and that sometimes works. However, the steel weight, the weight of the steel is 490 pounds per cubic feet. Okay, so you require some cranes, some welding, some drilling to get the holes for the bolts, and you require some machinery to tighten the bolts to the proper torque. So it's a much expensive adventure to do it that way. With the fibers, the fiber weight almost nothing. In fact, the strength to weight ratio is incredible. It's very lightweight. So it's very easy to take to a place, cut it, apply the epoxy, and then just place it. It's extremely easy in comparison to just using the basic methods. But I mentioned also a little while ago that in many cases we are working with a combination of traditional methods with the FRP methods. Like I mentioned, fatigue doesn't reset back to zero when you weld the crack. Right. However, you weld, you close the crack, you avoid the corrosion inside the crack, which also causes some issues, but then you strengthen the cross section such that crack will not initiate again by strengthening the cross section.
And so it's basically healing the structure.
Perhaps, yeah, exactly.
Setting it back to its original strength.
That's correct.
And so what about cost? How does the cost of FRP compare to traditional methods?
Let's use an example. Okay, we fix the pinto sockets. We fix the pinto sockets in Lock and Dam 1 and 2 on the Black River along Alexandria, Louisiana, with Vicksburg District. The cost was about $35,000, materials and labor, for a week of labor, and it took just less than a couple of days to repair them. If you go ahead and you need to create a new pinto socket, the cost is hundreds of thousands of dollars in comparison. So
that's a huge cost savings.
It's a huge cost saving. That's exactly right.
And so it's so let me get this straight. So what you're saying is FRP is cheaper, better, and faster.
That's faster to repair. Yes.
Faster to repair, and it also helps reset the durability of the structure.
Yeah.
And so that is amazing. So you have some of it with you. Can you show us some of what you brought with you today?
Oh, this is just a little plate with basalt fiber, quite directional basalt fibers. This is one of the samples that we created to do some material testing. This was done in our construction research lab up in Illinois. So basically, if you think about the size of this plate, this weighs about 1 pound or 2 pounds, and the same size of a plate of steel, 3/8 inches in thickness, is about 40 pounds. So that's kind of a 2 pounds versus 40 pounds. So, and this is just in a small plate.
Right.
Typically,
and so
you need much larger plates.
Right. And so this is, incredibly light. And so that is incredible.
Yeah.
And so easy to install.
Easy to install.
And it's cheaper.
It's cheaper.
And it's faster to install. And so I want to remind our audience, I'm sure that you have questions about how FRP can be applied to some of your engineering projects. And so be sure to put those right in the comments. And if you're not watching live, and if you're going back and watching this again after this has aired, we will ask Dr. Riveros those questions and get those answers back to you. And so these repair techniques have been deployed, like you said, to several districts across USACE, across the nation. Where have you and your team performed repairs, and what are some of the results since those repairs were made?
Thank you, Shelley. The first time we implemented this repair was 9 years ago, a little bit over 9 years ago in Old Hickory, Lock and Dam. And we repaired about Well, in three different locations. Locations with cracks that were lower than 2.5 inches long. Those cracks were untouched and just put the patches on top. And those cracks that were longer than 2.5 inches long, we gouge, re-weld, and then apply the patches. And in other locations that didn't have any cracks, but knowing the state of stresses, we consider that applying the strengthening of that cross section will help to avoid any potential for crack initiation. So the Old Hickory. Last week we went down to Old Hickory. It was the first time it was the water after we installed, and what we found out is that the fibers were in excellent conditions, like brand new conditions, almost incredible, not debonding whatsoever. But it has a couple reasons for this. One is that the district did protect the fibers by painting them, painting the areas of steel that were in the base metal. You have to repaint that to avoid the corrosion, but also they painted the fibers. By doing that, they also help, to keep the fibers away from the harsh environments.
Right. Very good. So we're going to go now to our audience questions to see what they have to ask you. And so the first audience question is, can you provide a brief history of your research on using FRP for repairing corroded steel girders in hydraulic structures? So can you give us a brief history of your research in regard to corroded steel girders in hydraulic structures?
Yeah, the corrosion research started about 3.5 years ago. And what we have done is that we have done experimental testing in lab conditions of wide flange beams, also known as I-beams.
I-beams.
So, yeah, in a 4-point bending condition. And what we found out, and the interest was not so much of gaining the strength, it's just more about the ductility of the structure. And what ductility is, once the steel reaches the yield strength or the elastic capacity, then it goes into the plastic mode.
That's right.
Where not all the stress will be not all the strain will be recovered. So how much ductility we're gonna lose? Because carbon fiber is a little bit stiffer than the steel. However, basalt is much elastic than the steel. So ductility was the interest, and those results are already, in a TR and in a journal article in the structural engineering journal. However, that's the first part. This year we are conducting experiments with true corrosion. In the first set of experiments, we grind a quarter of 10% of the steel, 10 to 20% of the steel. So it was what we call mechanical corrosion. This year, we actually developed the corrosion, cathodic corrosion, and we allowed the steel to corrode truly. Typically, the steel doesn't corrode uniformly. In some cases, sometimes it corrodes much more in one section than in others. So that's the idea. And now we are performing the experiments. That's the first thing. Second, we have performed a significant amount of numerical simulations also in our high performance computing center in beams of the size of typical beams of miter gates, 40 to 50 feet long beams. And we did some corrosion, 10, 20, 30%, up to 50%. From those results is that we can say that we can repair the corroded section up to 30% and bring it back to the normal state. The first time this has been performed for corrosion was in Overton Lock and Dam tinter gates. Those tinter gates, all the tinter gates in our country have an effect that is called the washing machine effect. So the sediments start scratching the painting. When the paint is gone, oxygen and water, start the corrosion process. But these gates are not inspected or dewatered constantly because they need to be used to maintain the pool elevations on the waterways. So these gates are heavily corroded. So the Vicksburg district under Mr. Ronnie Morrow, they strengthened. In fact, it's one of the pictures that was shown a little while ago. He strengthened the lower girder, which is the one that takes the majority of the tensile load or the load. He strengthened with FRP. It was about 20-30% corroded. He put 2 layers of carbon fiber, reinforced polymers, and that gate is still functioning today.
Wow, that's amazing. And so, what prompted you to explore FRP? Like, what prompted you to want to even go into this type of research?
That's a very interesting. You know, my PhD was in reinforced concrete. So in reinforced concrete, fiber reinforced polymer have been used extensively to repair reinforced concrete beams that have the tensile reinforcement is heavily corroded. So FRP is used to provide the tensile strength that have been lost by the corrosion of the tensile reinforcement. And it's been used for a significant amount of time. So when we start looking at that, we say, why we don't do that with the steel?
Right.
What is the problem? So when we start looking at the research done on this area, all the experiments were in the very small coupons. Yeah, they gave good results, but small coupons, which doesn't correlate to our large structures. So then we were able to get some funding for the navigation system research program, and we were able to do large scale testing, 1 meter by 1 meter plates with center cracks, with different configuration of FRP repairs, and with a 55 megapascals or AKSI of fatigue stress range, which is considerably large for a testing, and it can be analogous if you scale up that plate, analogous to the stresses that our structure is seeing. Okay. And based on that, we say, whoa, it works. It works. So first of all, it was the interest that it was being done in concrete. Why we don't do it in steel? We have a potential good use of this methodology for our navigation structure. So let's do the testing.
Wonderful.
And the testing was done on the water. And we even put a propeller with sediments as well, hitting the repair. So it was done as similar as possible to what our structures see in the field.
Wonderful. So our next audience question is, why is ERDC's FRP research important for the field of civil engineering and infrastructure maintenance?
Well, it's a couple things. I do believe that it's every 10 years to 15 years, the steel structures are repainted. But once you dewater, what you find is the significant amount of corrosion in some cases, some fatigue cracking, right? And like we have talked about that in a while. But by using FRP for maintenance, right? Mm-hmm. You have two main benefits if we want to talk about it. One, of course, the strengthening and the reduction of the crack propagation, but also by isolating that steel from oxygen, you reduce the rate of corrosion almost to zero.
Wow.
So it acts like a protective system, in other words, the painting system, but because it's much stronger, it's well bonded to the steel, that section of the steel will almost see no corrosion whatsoever.
Oh, that's wonderful, which therefore extends the life. Extends the life of the structure.
And reduce the corrosion, therefore,
that's right.
In fact, it reduces the cost of maintenance as well in the future.
Right.
Yeah.
And reduce the cost of maintenance, which reduces the cost, of maintaining it. And so how does FRP perform in extreme environments, like extreme hot or extreme cold environments?
Yeah, that's a very good question. The melting point of carbon fiber reinforced polymers is about 250 degrees Celsius. The melting point of basalt fibers is about 1,500 degrees Celsius. So that's extreme weather conditions. But that's not the important part. The important part is the installation. The curing process must be, the temperature must be about 70 degrees. Once it's cured, and once everything is cured, it performs extremely well. So such that the important part is the curing process during the installation. Right. If the installation is done properly, it has all Hickory, which is in Nashville, Tennessee, they see significant amount of weather changes, hot Absolutely. And cold, and it's still intact. We just repaired some pinto socket at the Sioux Locks, so we're going to see how that performed on that extreme cold weather conditions. But under hot conditions, it performed really well, and I think on the colder conditions as well.
Right. So our next question is, have you ever tried using graphene modified basalt fiber epoxy composites in making stronger bonds and repairs? So let me repeat that one more time. Have you ever tried using graphene modified basalt fiber epoxy composites in making stronger bonds and repairs?
No, I have not, but it will be a good idea to do some testing and see how it performs in comparison to what we have done so far. So it will be something very interesting to investigate as well.
Right. So right now you have been doing the basalt and the carbon. Mm-hmm. Okay. And so our next question is about collaboration. So have you been doing this research? Is it just ERDC doing this research, or have you had any collaborative partners?
Well, for example, like I mentioned before, when we developed the plates to do the experiments, so the material testing, we have some help from the Construction Engineering Research Lab in Urbana-Champaign, the polymer groups over there. Mm-hmm. Also, we work closely with Professor Mahmoud from Colorado State University, and I use his laboratory to do the experimental testing of the plates as well as the beams. So it's not just us. Also, some professors from University of Puerto Rico have helped us developing some numerical simulations for corroded members repair with FRP as well. And because, as you know, UPRM has a professor that from Georgia Tech that is an expert in fiber reinforced polymers as well. So we have used different expertises in different locations.
That's right. And our next question is, these repairs have been deployed on freshwater inland navigation structures. Can these be used in marine or saltwater environments?
Yes, they can. Some of these repairs have been done in all rig pipes underwater and using similar approaches. Sometimes they take the pipes out and they repair them and they bring it back underwater, and it does appear based on the literature that they have done. They perform quite well. So yes, they can use in saline environment. The most important thing is that the repair has to be on the dry.
Right.
So that's kind of
the issue.
The important issue, yeah.
And so the next question kind of follows up on that. It says, we've talked a lot about hydraulic steel structures. Are there other uses for FRP?
Well, it can be used in any infrastructure. I said that it started with reinforced concrete.
That's right.
So we can use it in military infrastructures, right? Mm-hmm. Buildings, right? Or hangars.
That's right.
So it can be used on those. It can also use in perhaps in some military applications. We just need to see the application and do the structural analysis to be sure that it's going to work. But certainly it can be used in any type of infrastructure.
Right, including our installations.
Installations, correct.
Absolutely. And so my next question from the audience is, let's see here, I'm a little behind. When you talked about collaboration, do you work with any other labs at ERDC?
Well, directly I haven't. I have worked a little bit with the Construction Engineering Research Lab. However, I've been in little communications with the Concrete Material branch of Geotechnical Structures Laboratory, because they have used a significant amount of different fiber reinforced polymers to do more like blast testing, energy dissipation, or bullet penetration, those type of work. So they have some expertise in that area as well, different than what we have. So I think I need to sit down and have a serious conversation with those folks to see what they know that we don't know and what we know that they don't know.
Absolutely. And so ERDC is doing lots of research with FRP in many applications.
Many applications. Yeah.
Yes. And so, I love this question. It says, you talked about happy steel atoms. Can you explain what that means?
No, it's just when the steel is sandblasted at the atomic level, of the steel, the atoms become very fluid and movable. They move quite fast. So some of the research that we have read indicates that the steel adhere much better to any surface that you put it together than when you grind it. So that's what I mean. It's at the atomic level. Right. More than that, I don't know. But based on what the research says, indicates that by sandblasting, the atoms become quite happy and they want to adhere better. Right. And it has been proven that they attach much better.
And attach much better. And so, can you tell us a little bit about your part in this and all of this research? Tell us a little bit about the numerical modeling, the modeling side of your research.
Yeah, thank you. That's a very, very interesting question. We like to perform, when we go to a field and to do an inspection, we like to do two things. If it's fatigue crack, we like to do a fracture assessment using fitness for service. We also like to do a 3D numerical simulation of the problem, of the existing problem, simulating the crack and understanding the state of stresses. And then we actually implement the repairs numerically to see the benefits of the repair prior to the implementation.
Right.
So that's typically what we do. At this moment, for example, we're working with Abilene Falls Dam lift gates. And those lift gates have some issues of corrosion, fatigue crack, as well as delamination. Seattle District has contacted us and they want to do a full 3-dimensional FEM analysis. They want the repairs of FRP, but we're doing the numerical simulation now. We're going to do the simulation with at least some deteriorations without any repairs, and then with the repairs to see how far we can get, how far or what reduction in stresses the steel will see when we apply the different layers.
And so I want to ask you a little bit more about that. So what is, when someone from the district comes to you and they're like, hey, we want this to be repaired, can you explain the importance? And because a lot of times people hear numerical model and they think, oh my goodness, the cost of this project just went up. Explain how the numerical modeling is actually cost effective in the end.
If we do not perform the structural analysis, then even though we know that the FRP will help,
right,
even if you put it on,
that's right,
we don't know how much help we're gaining,
right,
or how many layers do we need of FRP.
How to do the layups.
How many? 1, 2, 3, 4, 5. Do we need to do it in the entire girder, 25, 40 feet long sections? What do we need? The structural analysis and the FEM give us that choice. We can see the full state of stresses of the structure, where the highest stresses are, where the fatigue cracks are. If the fatigue cracks have to be gouged and re-welded and repaired, or they can barely be just put the FRP on or not.
Right.
So it's extremely important to perform a structural analysis prior to the repairs.
Prior to the repairs.
It will make the repairs last longer, because we're going to know exactly
how to do
what we need to do, and exactly how much gain we're getting out of the FRP repairs.
And eventually you would know from that the life expectancy now of the structure, because it's being reset.
Exactly.
And so now you know when you're having to do an analysis and make database-driven decisions on maintenance, that plays into this, which in turn would reduce the cost of maintenance.
Exactly. So always a little bit cost ahead of the issue, but in the long term, it will reduce the cost of maintenance. Right. So it really is going to be very, very cheap.
Right.
When you do a little bit of work ahead of time.
That's right. That's right. It saves
wait
a
until
lot of money in the end. That's exactly right. So pay a little bit now or a lot later on.
We spend a lot of money. The Army Corps spend a lot of money on schedule closures of our lock and dam systems. Some of the issues are the ones that we talk about with the gates, right? So we can avoid on schedule closures on our lock and dams due to corrosion or fatigue cracking then we're saving a significant amount of money. It costs about between $250 to $1 million a day to the water, to have the log dewater.
Dewatered.
So.
Right. So it's a big deal. So
It's
it
a significant amount of money.
saves a significant amount of money in the big picture. So our next question is, if this solution is less expensive and restores steel structures back to full strength, what are some of the reasons for still using the traditional solutions?
That is a very good question. We have to go to the district offices and communicate the findings of our research, because at the end of the day, the district offices are in charge.
That's right.
Of the maintenance and the operation of the structures. They are the ones that will decide what type of methods they're going to use to repair their structures. However, the more we implement the methodology and the more we have implemented it, the more calls we're getting, because people are seeing how things are working and the benefit of using the FRP in comparison to the traditional methods. So in many cases, we have to go and chat with the district offices, chat with engineers, chat with the chief of engineers, talk to them about our research, sharing all our publications, sharing our journal articles, sharing everything that we have done, where we have done it, and the benefits. In that way, they get kind of like, okay, let's give it a try.
I love it. And so it's a lot about communication and getting the word, spreading the word, which is one of the reasons we're doing this today. All right. So our next audience question is, how do you determine how much fiber and the type of fiber to repair a crack or corrosion?
The type of fiber, we can use either basalt or carbon fiber. Let me talk a little bit about those two material properties. Yes. Okay. The main failure mechanism of this repair is debonding. Okay. However, debonding, it doesn't become an issue when you have larger surface that have been implemented, because the carbon fiber is so stiff that it puts a significant amount of demand on the adhesive and the bonding. In comparison, the basalt, in fact, let me talk a little bit about, we're talking about with engineers. So the carbon fiber has the modulus of elasticity a little bit larger than the steel. So it's a stiff. However, the basalt is about the modulus of elasticity of aluminum. So it's very elastic. And by being elastic, places much less demand on the adhesive. So it debonds much less. So depending on where we are and the state of stresses and what we've seen, we can use one or the other. However, experimentally, we have proven that we can use either one of them, and both of them will provide infinite fatigue life on plates. So
it could be either one, but you're looking at it once you've done the structural analysis of which one is the best fit.
Best. Exactly.
And so the next question is, does FRP have any military applications?
Well, we talk about the installations, right? Military installations. That's one application. We need to see what kind of deterioration they have and what needs to be done, and perform the structural analysis. That's for sure. It may have other applications for other military, aspects. However, every case is different, so we need to look at the case. It's a case-by-case basis, and then do the analysis and see how it's going to work.
Anything that has fatigue
or corrosion,
which is a lot of stuff in military applications. So anything that has cracking, fatigue cracking, or corrosion, it could be a vehicle or whatever, anything that has that, FRP has a potential solution. And so the next question is, are there any ongoing or planned projects that aim to further test and refine FRP repair techniques you have developed? So let me ask that one more time. Are there any ongoing or planned projects that aim to further test and refine FRP repair techniques that you have already developed?
Well, right now, we are doing field work. Which doing the numerical simulations and the implementations and so on. But our funding for our work unit, for corrosion work unit, we started with fatigue and fracture.
Right.
About 10 years ago. Fatigue and fracture concluded that we started with the corrosion phase of the project. This year, the corrosion phase of the project ends. So I hope I can get more funding to do the refinement and to do some more testing with different fibers, perhaps,
Right.
and different applications as well. So
Very good. And so our next audience question is, you talked about FRP in extreme environments. How do you ensure the durability and effectiveness of FRP repairs under dynamic conditions of river environments? So how do you ensure the durability and effectiveness of FRP repairs under dynamic conditions?
yeah, let's talk about a particular project. Pickwick tinter valve. The tinter valves typically, when they open, they see supercritical flows. This tinter valve has a significant amount of vibrations and cavitation. So let's talk about those dynamic loads. Okay, so in this particular case, Pickwick, the stroke arm fracture, completely fracture. They put it back together and they weld it. Okay, they put a horseshoe of about 1.5 inches in each side and tap welded, which is the worst thing you can do for a connection of a steel structure. Tap weld will generate is the worst fatigue category, and crack will initiate very, very quickly with that type of vibrational dynamic loading. Okay, so we went there and put the FRP layers. Instead of using 2 layers, that typically is what it demands, we use a 3rd layer that covered the first 2 layers to protect the 2 layers that are providing the strength. And then we also soften the edges to avoid any high stress riser locations. Additionally, we cover the top layer with another layer of adhesive, protecting the top layer as well. So it's many things that we can do to protect the repairs under dynamic conditions.
And that's amazing. So have you reviewed earlier applications ERDC has done with FRP to evaluate how it has endured?
No, I have not, and I know it may be some literature out there, and I need to look at it. However, I do believe that the best case is all hickory.
Yes.
It's a true case. It's under the harsh environment conditions that our river waters are, or waterways are, so best case than that, is difficult to find.
Right.
It may be other reports that they had looked at it in detail on the laboratory conditions for different chemicals or so on and so forth. However, the best test is 10 years and it's still
Right.
going.
And it's been how many years?
Almost 10 years.
10 years. So it's been a decade, and the structure is still like it was the day you repaired it.
The repairs are still like brand new.
That is amazing. And so since ERDC's first use of FRPs, what have you learned over your career? Well, you've had a longer career than FRPs, but tell us a little bit about what you have learned through all of this.
Interesting enough is that I was more geared towards look at basalt.
Oh, really? Okay.
Than carbon fiber, but it's hard to just look at one without looking at the most common fiber that is used. That is carbon fiber. So the professor from Colorado State, he said, no, carbon fiber is better. I say, no, basalt is better. so once we did the testing, both of them performed similar.
Yeah.
So
it's a tie.
It was a tie. So anyways, it's incredible that we can find such a lightweight, fiber that can perform as well to do repairs and at a lower cost in comparison with others. That's kind of the main message in here. Mm-hmm. We can strengthen our structures, our deteriorated structure, bring it back to the original stress instead of stresses at a lower cost in comparison to other methods. If we do that with all our infrastructures, we can have lock gates, and dam gates that last for a long, long, long time.
Because there's no way we can financially as a nation
build new ones.
Yeah. I mean, there's not enough money.
It's not enough
and so having a solution that is better, faster, cheaper, and that heals the structure is really a game changer when you're talking about maintenance.
In other words, we're extending the life of the structure.
Yes, absolutely. So a design life of 50 has now become a design life of, say, 75 or even 100.
It's hard for me to kind of quantify it that way.
But when it sets back,
we extend the life.
You're extending the life. You're extending the life and giving us more time to make better decisions about what needs to be maintained and rack and stack the projects according to what is needed, instead of having to be forced to repair all of these structures at the same time, which in turn saves the United States money. And so real quick, can you, if we sat down 5 years from now or 10 years from now, what do you see the future at FRP?
Well, I think that we are starting, the districts are starting to catch up with the research.
Yes.
And we're getting more calls. I think we're going to have a significant amount of our navigation gates repaired.
Yes.
With FRP and in really good standing and condition based on this new research that we have come up and we have developed here at ERDC. So I'm expecting that more districts want to use the methodology in different locations, and I think many other districts will be using this.
Do you see it being used beyond USACE?
Oh, absolutely. It's being, the bridge industry, they were very afraid of using FRP because of the debonding conditions, and they have looked at, and now since we published our first 2 journals in structural engineering, many professors are looking at that for bridges, for other infrastructures. So it's starting to catch up also with the community.
Right. That is amazing. And so thank you so much, Dr. Riveros, for Guillermo.
We've got an hour. Oh my God.
We do. It went by fast. It's so exciting to talk about FRP. The time flies. Yeah. It's not just happy atoms, it's happy people getting to discuss FRP. And so I want to remind our audience that we'll be back here next month. And if you have any questions that we did not answer, just put those right there in the comments and we will get back to you. And we'll get back to Dr. Riveros and we'll have those questions answered. We also have a fabulous podcast. And so if you would like to know more about ERDC's technology, you can go to the poweroferdcpodcast.org on any of your favorite podcast players. Until next time, stay curious.